Hello everyone. Have you ever wondered why an ice cold Coke can make your teeth hurt while the same room temperature bottle feels fine? In physics, we say temperature is the measure of how hot or cold something is, but here's the twist: hot and cold are relative. A kettle with boiling water simply has a higher temperature than a box of ice, just like someone tall compared to someone shorter. It's all comparison. Now, our sense of touch. Completely unreliable. Touch a metal spoon and a wooden spoon in the same kitchen, both at the same temperature, but the metal feels colder. That's because it conducts heat faster. So physicists don't trust fingertips, we trust instruments. A thermometer uses a property that changes predictably with temperature, like the expansion of mercury or alcohol inside the glass tube. That's how we quantify hot and cold in numbers measured in Kelvin, the SI unit of temperature. Alright, now meet temperature's energetic cousin, heat. Picture this: you pour steaming tea into a cool porcelain cup. A few minutes later, both are warm. What just happened? Energy moved. Heat is energy in transit, moving only because of a difference in temperature. It always travels from hot to cold, never the other way. In the language of physics, we say Q equals m times S times delta T. Here, Q is the quantity of heat in joules, m is the mass in kilograms, S is the specific heat capacity in joules per kilogram per Kelvin, and delta T, read as change in temperature, is measured in kelvins or degrees Celsius. So whether it's your tea cooling or ice melting in lemonade, energy is just balancing the temperature scales, like financial equality in the thermal world. Here's a tricky question. Which holds more heat, a cup of boiling water or an entire swimming pool that's just a little warm? Believe it or not, it's the swimming pool. That's because temperature measures average kinetic energy per molecule, while heat measures the total energy in motion. The pool has trillions more molecules dancing, even if each one jiggles slower. Temperature is an intensive property. It doesn't depend on how much stuff you have. Heat is extensive, double the mass, double the energy transfer. Look at the diagram. Body A at temperature Ta greater than body B at temperature Tb. Heat flows from A to B until both reach the same temperature. And remember the units: temperature in Kelvin, symbol K; heat in joule, symbol J. So next time someone says, "This pan has a lot of heat," you can grin and say, "Nope. It only transfers it." So, when does this energy traffic finally stop? When both systems reach the same temperature. No temperature difference means no heat flow. This is called thermal equilibrium. This idea is summarized beautifully in the Zeroth Law of Thermodynamics. And yes, it's called Zeroth because scientists realized it should come even before the first law. It says, if body A is in thermal equilibrium with body B, and body B is in thermal equilibrium with body C, then body A is also in equilibrium with body C. This simple sounding statement is why thermometers work. When you dip a thermometer in hot soup, both eventually reach the same temperature. The thermometer's reading is reliable only because of this law. So, temperature is like the referee ensuring every object plays fair. Once equilibrium is achieved, no team, hot or cold, wins. Let's crunch some numbers, gently, not brutally. Suppose you have half a kilogram of water, that's m equals 0.5 kilograms, and you heat it from 20 degrees Celsius to 30 degrees Celsius. The specific heat capacity of water is 4.18 times 10 to the power 3 joules per kilogram per Kelvin. Using our equation, Q equals m times S times delta T, substitute the values. Q equals 0.5 times 4.18 times 10 to the power 3 times 10. That gives Q equals 2.09 times 10 to the power 4 joules, or roughly 20.9 kilojoules of heat energy. So your kettle just supplied about 21 kilojoules to make that small temperature rise. No phase change, just faster jiggling water molecules, each celebrating the extra energy. Alright, let's wrap this up like a warm blanket. Temperature tells us how energetic each particle is. It's a measure of hotness. Heat is the energy that moves from one body to another because of a temperature difference. When two bodies reach the same temperature, they're in thermal equilibrium, no more net flow of heat. Always remember the key units: Kelvin, spelled K, for temperature, and Joule, spelled J, for heat energy. Everyday examples prove it: ice melting in your drink, tea cooling on your desk, or metals expanding when heated, all are just manifestations of this energy exchange. So, the next time your coffee cools down, smile and say, "Thermal equilibrium achieved." That's not physics homework, it's nature doing its job. Thanks for learning with me. Stay curious, stay warm, and I'll see you in our next session with another hot topic from the world of physics.